Hello? Hello? Hello?
Good afternoon, madam.
Yeah, good afternoon. Am I audible? My screen is visible?
So screen is not visible, ma'am.
Okay, I'll share. Is it visible now? Hello?
Yes, ma'am. Yes, ma'am.
Yeah, it is visible, right?
Oh.
Okay. Okay, good afternoon, everyone. In the last
Good
class,
afternoon, madam.
yeah, in the last class, we have discussed about factors affecting chemical shift, and I think we completed it, but still I'll just revise once again the factors affecting chemical shift. Okay. So main factors affecting chemical shift of C13 nuclei are electronegativity, hybridization, anisotropy, heavy atom effect, hydrogen bonding, isotopic effect, solvent shifts, electron deficiency, and effect of pH. I'll just go through it very fast because we've already discussed it. Just want to brush it up. So, one is hybridization. From the chemical shifts values in the C13 NMR, we will be able to identify whether we have sp3 carbons present, sp2 carbons present, and sp carbons present, so because they have got different chemical shift values. And electronegative groups in the molecule will influence the chemical shifts, as in the case of PMR. The more the electronegativity of attached group or atom, more will be the chemical shift. Since here directly the carbon is attached to electronegative group, the shift will be more. I have given you example. See, ethane is this much. When it is attached to OCH3, it is shifted downfield. Similarly, it depends on the electronegativity. As the electronegativity of the attached atom or group increases, chemical shift increases. See, fluorine attached carbon is showing 79.3 ppm. And anisotropy means the the magnetic field generated by the circulating pi electrons is not same around the molecule. It is more at some places and less at some places. That is why we call it anisotropy. Isotropy means same around and same everywhere. Anisotropy means it is not same. So like this, here in benzene, pi electrons, that ring current is circulating and that generates a secondary magnetic field. It is anisotropic because it is upfield, it is less. I mean, effective magnetic field is opposing the applied magnetic field above and below the benzene ring, and at the periphery, it is reinforcing the applied magnetic field. Therefore, the carbons present above or below the benzene ring or any aromatic ring, which is having ring current, which is aromatic, then will show a field shifts. For example, in paracyclophanes, I gave you an example. The carbons that are present above or below, like here or there. I'm just showing you benzene ring here, but paracyclophanes, the 1,4 positions in benzene ring are connected by carbons, the aliphatic chain. Suppose the carbon that is lying just above the ring current, this one will show upfield shift. So similarly, alkene, by just one double bond, it is also upfield above and below the double bond, and at the carbons at the alkenic carbons, it is downfield shift. That is the reason why ethylene shows 123.3 ppm shift, and any alkene will show the shift accordingly. Similarly, carbonyl and acetylene is something different, because at the carbon it is upfield, and above and below the acetylenic triple bond it is downfield. Okay, so this is anisotropy. We discussed the examples. See, this is the one. It is just lying above the benzene ring. That is why it is shielded. Upfield shift. This is also shielded because of the ring current. This is up above the ring current, so it is upfield shift. And carbonyl carbon aldehyde is downfield, and acetylenic carbon is upfield. See, it is like triple bond, so that carbon is shifted upfield. And benzene I have given you for reference. This benzene value and ethylene value you need to remember. Sometimes in the examinations they may be asked in the competitive examinations. Okay, just to compare. And then mesomeric shifts means electron delocalization effects. For example, electron donating groups are attached to benzene ring, that will increase the chemical shift at ortho and para positions. Therefore, in anisole, phenol, and aniline, and all those molecules, ortho and para carbons are shifted upfield. Suppose if the group is electron withdrawing, it will withdraw the electron density from the aromatic ring, and it will decrease the electron density at ortho and para positions, resulting in downfield shift. For example, nitrobenzene, nitro group is electron withdrawing. Acetophenone, COCH3 is electron withdrawing. Ester group and nitrile group, all these groups will decrease the chemical shift at ortho and para carbons. So electron donate as a general rule, you can remember in alkoxybenzenes, phenols, aromatic hydroxy compounds, in all these cases, OH and O are electron donating, and that will increase the electron density at ortho and para positions. Therefore, they are shifted upfield. Similarly, aniline, substituted aniline and substituted anilines, that is also electron releasing group, that will also increase. In aniline, for example, ortho and para carbons are shifted upfield. I showed you the examples in here. See, some more examples here. That is about benzene ring. Here, vinyl ether, see, electron mesomeric effect. Electron is moving towards double bond, and alpha and beta. Beta carbon is getting electron rich. Therefore, beta carbon is shifted upfield. See the values. Similarly, in alkynyl ethers also same thing. Beta carbon is shifted upfield. Means lower chemical shift value because they are shielded. See, this is electron withdrawing effect. Alpha beta unsaturated carbonyl compounds. It is moving away from the beta carbon. The electron density is moving away from the beta carbon. Therefore, this will become electron deficient. Therefore, see the difference. 136 in acrolein. And methyl vinyl ether also, methyl vinyl ketone also, it's shifted downfield. Similarly, cyclohexenone, see, beta carbon is 150.6, and cyclopentenone, beta carbon is 165.1. That is due to the electron withdrawing effect of the carbonyl group. Similarly, in all these cases, whenever, just as a general rule, you can remember that any electron withdrawing group attached to double bond, it will decrease the electron density at beta carbon. Therefore, that will have higher chemical shift value. And in benzene, also electron withdrawing groups take away the electron density from the benzene ring and decrease the electron density more at ortho and para positions. Therefore, those ortho and para carbons are shifted downfield. Okay. See, I have given you examples. And aniline, you just compare aniline, ortho and para. Electron density is more. Therefore, it is less than benzene. See, 116, 1.1 and 119. And here, also electron releasing. So ortho and para electron rich 114.1 and para 120.8. See here, benzaldehyde electron withdrawing. See, ortho 129.7 less than, more than benzene. Para 134.3 again more than benzene. 128.5 is benzene. Okay, and see benzophenone also same thing 130 ortho carbon and para carbon 132.3. Electron delocalization effect is more at para carbon. Therefore, para is showing more downfield than ortho carbon. You see. 133.8 and 134.5 for nitrobenzene. See, similarly, any electron withdrawing group attached to not only benzene ring, any aromatic ring that will shift the chemical shift, that will increase the chemical shift values. Downfield shifts are observed at ortho and para carbons. See, conjugation effect also has got increased electron density slightly. Therefore, this conjugated double bond will show upfield shift. And heavy atom effect, heavy atoms like bromine, iodine, or when they are attached, that will increase the electron density of the particular carbon. If more the number of heavy atoms, more will be the upfield shift. See, CH3Br 10, here 2 bromines are there. Actually, this is electronegativity effect. 1 bromine and 2 bromines. So it's more. Then you compare with the 3 bromines, it is down. See, it is upfield. That means this is heavy atom effect. From here to here, it is electronegative effect. From here to here, it is heavy atom effect. And from here to here, again, heavy atom effect. Whereas in case of iodine, heavy atom effect starts from the first iodine, first substitution itself. From methane, see, methane is minus 2.5, methyl iodide is minus 20. So upfield shift is observed with 2 iodines minus 54, with 3 iodines minus 139.9, and with 4 iodines minus 292.5. So heavy atom effect is really very much in case of iodine. Bromine also it is observed. Actually, iodine always, even 1 iodine also results in heavy, influences that chemical shift value. See the ipsocarbon, normal electronegative group, if it is attached, that ipsocarbon would have been downfield than, more, the chemical shift value of this ipsocarbon would have been more than benzene. But because of heavy atom effect, that ipsocarbon is upfield. So these are the questions generally asked in examinations, while the reasons and any competitive examinations like CSR and mainly iodine and bromine. You remember, first iodine itself results in a field shift of the ipsocarbon. The reason for the upfield shift of ipsocarbon in iodobenzene is. So they will give you different choices, and you should be able to identify that. That is due to heavy atom effect. Okay, and next, hydrogen bonding. I told you hydrogen bonding decreases the electron density around carbon, so it shifts the chemical shift to downfield. See, normal benzaldehyde 191.5 and orthohydroxybenzaldehyde C, because of the decreased electron density due to intramolecular hydrogen bonding, it is downfield shift is observed. So the chemical shift is at higher frequency. Downfield shift means higher frequency. Upfield shift means lower frequency. Okay. And next, isotopic effect also, though it is very small, it is also observed in case of deuterium substitution. Slightly more than hydrogen. When hydrogen is substituted, and if you compare like Cd to Cl2 and CH to Cl2, isotopic effect, the deuterium effect, upfield shift will be observed with deuterium substitution. This is mainly helpful in analyzing the spectra of deuterated samples. Same thing, same thing I have given you here. Yeah. Electron deficiency, I told you already, electron deficiency decreases the electron deficiency means it is the decreased electron density around carbon. Therefore, it is shifted downfield. That means higher frequency. See, normally, carbon signals are observed around 240 amps, no? And in case of carbonium ions, they will go up to 320 also, 350 also. Even 340, 350, even 360 sometimes maximum. Okay, 330, 340, that range will be observed for carbonium ions. Similarly, carbon ions will show upfield shift. Now, these are couple factors affecting chemical shift. You need to you be thorough with these factors, because you should be able to identify which one will come upfield when you compare with the reference sample, or simply if it is an unknown sample also, you should be able to predict where exactly the chemical shift comes. So that will help you in solving the problems. Okay. Now, we will discuss now about couplings in C13 NMR. See, couplings you already have come across in Proton NMR. What is coupling? When nuclei, magnetic nuclei with a different non-equivalent non-equivalent magnetic nuclei, means chemically non-equivalent magnetic nuclei are in the vicinity. When they interact with each other, and they will undergo spin-spin splitting, and results in the splitting of the signals, which we call coupling. They couple, and therefore they result in splitting. So in case of Proton NMR, for example, ethanol or ethyl chloride, you see CH3 protons and CH2 protons. So two types of protons are there. But they will not be observed as singlets. Simple methane Proton NMR, if you see, you will get only one singlet. When it is attached to CH2, ethyl chloride, CH2Cl, it will not be observed as singlet. Methyl signal appears as triplet, and CH2 appears as quartet. This you have learned in first year. Okay. So the same thing, that is due to spin-spin coupling. So Proton NMR also, CH3 and CH2 protons are chemically different, non-equivalent, therefore magnetically non-equivalent. Therefore, CH3 protons, that means protons, the nuclei of CH3 protons will interact with CH2 proton nuclei. That means they will undergo coupling, resulting in splitting of the signal in each case. CH3 and CH3, because of two neighboring protons, it will be split into a triplet. CH2, because of three neighboring protons, it will be split into quartet. 2Ni plus 1 rule. 2Ni plus 1 rule. Remember, 2 is N is the number of non-equivalent protons. I is the spin number, that is half, plus 1. So if 2 protons are there, 2 into N, 2 into half. So that means 2 gets cancelled, 2 plus 1, it becomes 3. So this you have already learned in Proton NMR. So similarly, C13 nuclei also undergo coupling when they are attached to magnetically non-equivalent nuclei. Here in this case, especially in organic molecules, generally we deal with protons. Proton also is magnetic, and carbon is normally connected to hydrogen, different types of hydrogens, and you have different non-equivalent carbons. So carbon can couple with hydrogen because of the interaction of carbon nucleus with hydrogen nucleus. And the principle is same as Proton NMR here also. So, like proton C13 also undergoes coupling with other magnetic nuclei, mainly here hydrogen, and it can undergo coupling with other magnetic nuclei like fluorine, P31, and even other magnetic nuclei also. They're also significant, they're also important, but not as significant as protons, because hydrogens are abundant in organic molecules. Fluorine also we can observe, but in only few fluoro compounds, and phosphorus also, the probability of the number of organic compounds with phosphorus is quite less, and especially when we are dealing with organic molecules, they will be. So they will be useful. But here in C13, you have two types of couplings, heteronuclear couplings and homonuclear couplings. Heteronuclear means the name itself suggests the couplings between C13 and other nuclei, other magnetic nuclei. So it can be hydrogen, it can be fluorine or P31, etc. So coupling between C13 and H1, we call C13 CH couplings, and coupling between C13 and other magnetic nuclei, we call CF, CP, and CB, etc. Depending on the magnetic nucleus that is attached to carbon. So these couplings are important. Heteronuclear couplings, CH couplings are important. I'll discuss them in detail. And homonuclear couplings means it is the same between the same type of nuclei, carbon-13 and carbon-13. So the coupling interaction between two carbon-13 atoms. This is quite rare in normal organic molecules because probability of finding C13 in adjacent, two C13s in adjacent positions is very rare because of the low natural abundance of C13. Finding one C13 itself is 1.1%. Finding two C13 atoms in the same molecule and that too in adjacent positions is quite rare. Therefore, homonuclear couplings are not normally observed in routine C13 spectra. But however, suppose if it is enriched sample, like we enriched the molecule with another C13 in adjacent position, then homonuclear couplings may be observed. So that will be actually sometimes in special cases when we are facing some problems in the structural elucidation, this type of labeling is carried out, and C13 couplings are homonuclear C13 couplings are also observed. Okay. But normally this is not observed. The same thing it is shown here. So that most important couplings in C13 NMR, the coupling between carbon and hydrogen. Here also you can have three types of couplings: 1 bond couplings, 2 bond couplings, and 3 bond couplings. Even 4 bond couplings also may be there, but just up to 3 bonds, it's quite common. 1 bond couplings means what? Carbon is attached to hydrogen, directly attached. So carbon and hydrogen to which it is coupled is separated by only 1 bond. The carbon and hydrogen which are the carbon which is undergoing coupling to hydrogen, that they are separated by only 1 bond. That means directly attached hydrogens. So we call it J1CH. Normally coupling is denoted by J. 1 means 1 bond. So they are separated by 1 bond. Thus, the coupling nuclei are separated by 1 bond. And what are being coupled here? Carbon and hydrogen. That is a J1CH. J1CH means it is the coupling between carbon and directly attached hydrogens. So in simple hydrocarbons, J1CH couplings are directly proportional to the extent of S character and S character of the CH bond. So the percentage S character varies with the hybridization. Actually it is given by J1CH is given by a simple equation 500 rho. Rho is the S character. Suppose if it is sp3 hybridized, S character is 25%, is it not? So 500 into 25 divided by 100, that will be 125 hertz. So in methane, it is around 125 hertz. In ethylene, it is S character is sp2. So 33%, rightly. 33% means 0.33. So it will be 500 into 33 divided by 100. That will come to 167 point something. So 167 hertz in ethylene. So coupling constant between carbon and hydrogen is 167 hertz. In acetylene, you see it both are equal. 50% S character, 50% P character. So therefore 0.5. So 500 into 50 divided by 100, that will be equal to 250 hertz. So in acetylene, coupling constant J1CH is 250. And similarly, these are the parent systems: methane, ethylene, and acetylene. sp3 hybridized, sp2 hybridized, and sp hybridized. Suppose if it is attached to other electronegative groups, that also influences the coupling constant of CH bond. So the electronegative group increases the coupling constant, and the more the electronegative groups, if it is 1, it will have certain value, increases up to certain value, and if it is 2, that is additive. That means, for example, see, these values are especially very important to predict the S character of a particular carbon in the molecule, which in turn gives the hybridization state of that particular carbon in an unknown molecule. We can say whether it is alkenic or alkane carbon, alkenic carbon, or alkynic carbon. So that way we can identify. The values of J1CH are helpful in probing the extent of S character in a molecule. Okay. The magnitude of J1CH values also vary with the nature of the substituents, and it is largely additive. More electronegative groups, more will be the coupling constant. So for example, I have given you one representative example here. CH4, 125 Hertz like this, and CH3Cl, 1 fluorine attached, so 150 Hertz. So roughly 25 Hertz increase. And 2 chlorines are attached. See, roughly 50 Hertz, 53 Hertz increase, roughly additive. 25, 50, and 53. Okay, CHCl3, you see, it is again 3, about 75. So roughly 209 Hertz. So that way, the number of electronegative groups or atoms, the shift due to that. That means the increased value, it depends on the number of electronegative groups or atoms, like in having coupling constant. Okay. Similarly, I am giving you the effect of electronegative substitution is more when it is attached to sp2 hybridized carbon. See, the effect is there. In case of sp3 carbon also it is there. But it is more on when it is attached to sp2 carbon and sp carbon. See, one sp2 carbon attached and it has become 177 Hertz. Here it is 150 Hertz. So it is more, right? Isn't it? Because of the double bond, because of the S character. And this is about J1CH couplings, when the coupling between carbon and hydrogen separated by one bond, and that is simply given by 500 rho. Next, 2 bond couplings. 2 bond couplings means here carbon and hydrogen are separated by 2 bonds, 1 and 2. So vicinal coupling, it is similar to vicinal coupling in case of not vicinal, geminal coupling. Geminal coupling in case of Proton Nmr. Okay, 2 bond couplings, J2CH, because it is separate. J2 means the coupling nuclei are separated by 2 bonds. What are the nuclei that are being coupled? Carbon and hydrogen. So carbon and hydrogen, J2CH, like this. This and this are coupling. They are separated by 2 bonds. We call it J2CH. Suppose, see, another heteronuclear coupling is, it is fluorine. Fluorine. Hello? 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 Hello?
Hello, please carry on, madam. We are following.
No, you please answer, because here the power has gone. So I just thought internet got disconnected.
Okay.
That's why I
Right, madam.
Okay. So two bond couplings are, the carbon and hydrogen are separated by 2 bonds. So J2CH. Suppose I told you, heteronuclear couplings means the coupling between carbon and other nuclei, hydrogen, fluorine. Suppose if it is coupling to fluorine, we call it J2CF. Instead of hydrogen, suppose if you have fluorine here, we call it J2CF. Instead of hydrogen, if you have phosphorus, we call it J2CP. You understand? So this is the this is how we call these couplings. So J2CH means the coupling between carbon and hydrogen, which is separated by 2 bonds. This is usually small for aliphatic systems, and it is also influenced by the electronegative substituent and also the bond angle. This bond angle. Okay, the bond angle also has got electronegativity also. It influences the coupling constant. I'm giving you some examples here. See, this carbonyl carbon and this hydrogen, 26.7 Hertz. Here it is sp2 carbon, that is a coupling constant is slightly more. If it is sp3 carbon, it will not be that much, it will be slightly less. And see, this is also carbonyl carbon. I mean, this carbon and this hydrogen, 32.5 bonds. It is separated by these two bonds are separated. Two carbons are separated by carbonyl group. That also influences the coupling constant. Here also see 35.3, and here also see it's 61. See, it is triply bonded carbon. Triply bonded carbon, even the coupling constant is more because it is quite in the same plane. Okay, interaction is more. And here you see 33.2 hertz. So like that, the J2CH couplings are less than J1CH couplings, but they are important, especially when you have double bonded carbons, triple bonded carbons, aromatic carbons in the molecule. And same like J1CH, here also electronegativity and negativity of the attached substituent increases the coupling constant. 3 bond couplings. Again, similarly, the carbon and hydrogen that are being coupled are separated by 3 bonds, 1, 2, 3. It is similar to vicinal couplings in Proton Nmr. In Proton Nmr also same, no, neighboring protons coupled. So they are also, here also it is similar to vicinal coupling. So in Proton Nmr, that vicinal coupling is dependent on dihedral angle. Hope you remember it. And here also it is dependent on dihedral angle. The dihedral angle is the angle between two planes, CCC and CCH. If it is 180 degrees, then when the dihedral angle is 180 degrees, J3CH is maximum. When the dihedral angle is 0, it is little less than maximum, similar to 180 degrees. But if it is 90 degrees, the interaction will be very less. Therefore, it is minimum, sometimes even 0. They do not couple at all. Okay. So in alkenes, this 3 bond couplings are similar to vicinal couplings. They are very important, especially in case of aromatic compounds. For example, J1, the coupling between C1, 1, 2, 3. I mean the hydrogen on third carbon. The hydrogen on third carbon, that is J3 coupling, J3CH. So JC1H3, it is 11.1. JC2H4 means H4 means the hydrogen present on 4 carbon, and JC2H4 is 7.9. These are the values. So C2H6 means this carbon and the hydrogen present on 6 carbon. So this is also separated by 3 bonds. So these are the values. Okay. Similarly, and this just to make you understand, you need not remember any of these values, just ranges you just try to remember, as in the case of Proton Nmr. And it is similar to your vicinal couplings in Proton Nmr. So dichlorobenzene, some values I have given you. Furan also I have given you. C2H4. C2H4 means the C2 carbon and hydrogen present on 4th carbon. That means this one bond, this one bond, and this one bond. 3 bonds separation. So therefore, it is J3CH coupling. Vicinal coupling, similar to vicinal coupling, and which it is dependent on the dihedral angle. This is very important, especially in certain cases. When we see the examples, we will understand. Okay, and yeah, this is about heteronuclear couplings. I have discussed about heteronuclear couplings between carbon and hydrogen. Similarly, carbon can undergo coupling with fluorine. I mean, means, for example, CH3F is there. That CH3 can couple with fluorine. So then, what do you expect for that CH3? CH3, it couples with hydrogen also. It also couples with fluorine. CH3F, methyl fluoride. It couples with fluorine also. So what is that you expect? You get a quartet of doublets. Okay, because carbon couples with 3 hydrogens, it gives you a quartet, and which in turn couples with fluorine. So each line will split into a doublet. So you have a quartet, which is a quartet of doublets. Each line in the quartet will be split into 2 lines in methyl fluoride. So like that, you can, carbon can undergo with other heteronuclei also, like mainly fluorine, P31, important. So in case you have fluorine NMR also, I'll discuss what you get there. Okay. homonuclear couplings. Homonuclear means I already told you it is the coupling between carbon and carbon 13 and carbon 13. So probability of finding two carbon 13s in adjacent positions is very rare unless it is labeled compound and enriched compound. Enriched compounds may have two different two carbons in adjacent positions, C13s. So they can undergo coupling, and those couplings here also you can have J1C. J2CC and J3CC. So same in the case of J1CH, J2CH, J3CH. Here also two carbons. Two carbons are separated by one bond, this J1CC. So they are generally smaller than J1CH. So you can compare. J1CH are around 125 Hertz. J1CC are less, 36.9 only in case of this isobutane. And here you see 33 Hertz in case of ethyl propionitrile. So ethanol is 37.7, acetone it is about 40.1. So they are the J1CC couplings. When this is the coupling between this carbon and this carbon, okay, J1CC. Here carbonyl carbon or CC carbon is enriched, then it will undergo coupling. So 2 bond CC couplings are usually smaller than 3 Hertz in saturated aliphatic systems, but they are larger if the central carbon is carbonyl or acetylene group. That is what we have seen. Central carbon is carbonyl or acetylene. They will be more. Now, homonuclear couplings, 2 bond carbon coupling. See, this carbon and this carbon separated by 2 bonds, 1 and 2. 2 bonds. So this is J2CC. It is usually smaller, 3 Hertz in saturated aliphatic systems. So here the central, they are larger if the central carbon is a carbonyl group or acetylene group. This is what I mean. See, this is what J2CC. So this carbon between the coupling between this carbon and this carbon, but the central carbon is acetylenic, you see. So it is having 11.8. Otherwise, it would have been less than 3 Hertz. Here also you see these two. This is triply bonded carbon. Therefore, 33 Hertz. It need not be central carbon. You know, if it is central carbon, it is definitely more. If it need not be central carbon, like in case of nitrile also, it is more. And here you see that you can compare the difference. Here C1, C3. What is C1? C1. This is C1, C3. So they are separated by 2 bonds, 1, 2. Therefore, this is 2 bond coupling, and see the coupling constant is only 1.7 Hertz. Here no double bond or triple bond or double bond is there. That's why it is less than 3 Hertz. Whereas here acetylenic group is there, therefore it is more. See this, it is shown by stars because they are enriched. Normally it will not be observed. They are shown by stars here also. See, they are labeled or enriched with carbon 13. Then you can observe couplings, homonuclear couplings. And here also you can, even 2 bond carbon, here also you can have vicinal coupling like a J3CC. That also depends on the dihedral angle, but generally it's very less. So that is about couplings. Coupling, actually coupling constants are very useful, especially when in unknown systems to identify the hybridization state of the carbon, and also to know the angles, to know the stereochemistry, etc. But normally, as I told you earlier, coupling constants we only record SFORD, that means off resonance free coupling, where we get the splitting of carbons, but not the coupling constant. It's only residual coupling constant we get there. Okay, but in specific cases when it is required, we will record the coupling constant also, which will be helpful in structural elucidation for some specific molecules. Okay, now applications of C13 NMR. You know, spectroscopy means it has got a lot of application in structural elucidation, and C13 NMR also one such spectroscopic technique. It will give you a lot of information about the known molecule and even unknown molecule. To confirm the structures of unknown molecules, complex molecules, all this spectroscopic information is very important. Just a proton NMR is not sufficient. So C13 NMR also sometimes comes to our rescue, especially when you are solving complex structural problems. So it is very useful in structural identification and also sometimes structural assignment, and also for structure confirmation. We synthesize a molecule, we want to know whether the molecule we prepared is same what we expected or something different. Then also we will study all spectroscopic, we will do all spectroscopic analysis and interpret it and arrive at the conclusion. Generally whether we got the compound or not. If it's an unknown compound, if it is a known compound, generally we compare with the known samples, and that's how we will confirm the structure. Okay, so when there is ambiguity about the structure, then also C13 NMR is helpful. So it is very useful in identification of the structure, assignment of the structure, confirmation of the structure, to distinguish isomers, for structure confirmation, conformational analysis, to differentiate geometrical isomers, to study reaction mechanisms, to study the stability of carbonium ions, to study the dynamic equilibrium in some some reactions, to identify the degenerate rearrangements, to check the formation of carbon ions, etc. So we will try to discuss them in detail one by one. So C13 NMR is very useful to distinguish isomeric paraffins. It's usually very difficult. Why? Because, for example, you have N-hexane, methyl pentane, so like that, different isomers are there. Then all are aliphatic protons. So when you take proton NMR, you will get a second order spectrum and a complex multiplet of proton signature, which you cannot interpret easily, and which we will not be able to identify which is which. Whereas C13 NMR, as I already told you, due to the chemical shift range is very high, each and every known equivalent C13, each and every known equivalent carbon in the molecule will come as separate signal, and proton decoupled spectrum gives you all non-equivalent carbons as singlets, and they're nicely separated in the spectrum, and it is very easy to interpret. Therefore, these paraffins, especially where you have only carbon and hydrogens, and the chemical shift range is very small in case of proton NMR, and they undergo coupling, they will give you second order spectra. N-hexane, for example, heptane, N-hexane, octane, pentane also. All these paraffins, they will give you a very complex proton NMR spectra. Whereas if we record C13 NMR spectra, the spectrum will be simplified. We will be able to identify the number of non-equivalent carbons in the molecule. So that will give us, that will help us in identifying the structures. I'm just showing you. See here, why they are complex, why proton NMR is complex, due to the chemical shift, closer proximity, close range of chemical shifts of proton in aliphatic carbons or paraffins. In these isomeric paraffins, there will be too much overlapping of multiplets. Why multiplets? Because they will undergo coupling with each other. So complete complex pattern of multiplets will get. We will not be able to make out anything from proton NMR because of the overlapping of multiplets. Closer chemical shift range and also overlapping. In that also overlapping. So in a small chemical shift range, say 0.2 ppm, 0.3 ppm, you will get all the signals and that too multiplets. So we can't make out anything from there. Okay. But here in C13 NMR, we can get separate signals because of the chemical shift range. Showing you, see this example is just what is this? 1, 2, 3, 4, 5, 6, 7, 2 methyl heptane, 2 methyl 1, 2, 3 methyl heptane. So 3 methyl heptane you have 1, 2, 3, 4, 3-methyl heptane. You have how many carbons? Non-equivalent carbons? 1, 2, 3, 4, 5, 6, 7, and 8. All are non-equivalent. Why? Because there is no symmetry here. So 8 non-equivalent carbons. So how many signals you get? 8 signals you get. In proton decoupled spectrum, you get 9 singlets. So if it is SFORD, what do you get? How many quartets you get here? 1, 2, 3 quartets you get. And how many triplets you get? 1, 2, 3, 4. 4 CH2s are there. 4 triplets you get. And how many doublets you get? 1 doublet you get. So 1 doublet you will get, and 3 quartets and 4 triplets. So just similarly, you can compare another isomer, other isomer of this, no name. See, 3-methyl. Okay, 9, 8 only, no? 3-methyl heptane, octane. Next is octane. Just normal chain. In that 8 octane, how many signals you expect? This you can do some exercise and tell me how many signals you expect. So from that you can compare whether it is octane or 3-methyl heptane. Okay, how many signals you expect? No answer. Okay, try at home. See here, this is what 1, 2, 3, 4, 5, 6 hexane and 2-methyl pentane. So if you compare these things, see how many signals you expect here. How many signals in hexane? This same, this same. Okay, 1, this and this, 1 and 6 are same, 2 and 5 are same, 3 and 4 are same. So 3 signals you expect. Whereas here you see 1, 2, 3, 4, 5, 6 signals you get. Here there is no signal. Here 1, 2, 3, 4, 5 signals you get. So 2-methyl pentane will give you 5 signals, whereas N-hexane will give you 3 signals only. So from the number of signals in proton decoupled spectrum, you will be able to identify which isomeric alkane is this. And not only that, even if you record SFORD, you see here you have 2 methyl groups, so 2 quartets. Whereas here you have 3 methyl groups, so 3 quartets. And here 1, 2, 3, 4 triplets you will get. Here you have only 2 triplets and 1 doublet. 2 triplets and 1 doublet and 2 quartets. So not 3 quartets, 2 quartets, because these 2 are same. 2 quartets, 1 doublet and 2 triplets. So you will be able to identify. Similarly, it's values also I have given you. Yeah, see C1 and C4, C4. Not C4, it is C6. See, that is a print mistake. You check in your books also. This is taken from the book only. So you just correct. C1 and C6 are same. C2 and C5 are same. C3 and C4 are same. Actually, this change, interchange, 6 should go there, 4 should come here. Okay. Isopentane or 2-methyl butane. 2-methyl butane gives how many signals? 1, 2, 3, 4 signals, isn't it? Because these 2 are same. C1 and C, there is no, yeah, C5. We call it C5. See, this is chemical shift value. So C2 is this much, C2 is this much. So from here, see, they may give like like problem like this. N-hexane. 1, 2, 3, 4, 5. Pentane. Yeah. Pentane, N-pentane, and isopentane. Okay, so what is the formula? C5H12, isn't it? 5, yeah, H12, C5H12. Both N-pentane and isopentane, both the molecular formula is same, C5H12, but they may give you a chemical shift values. See, for example, you are getting chemical shift values like this. It will be 2, that is isopentane, or 2-methyl butane. Okay, you can identify the isomeric alkanes. Similarly, here also a question may come. 1, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So C6H14. I'm framing you a question. You just try to understand. It gives 1 quartet and 2 triplets. It gives one quartet and two triplets, and its molecular formula is C6H14. What is the structure of that alkane? No answer. Try at home and leave it. Okay. And then similarly, 1-chloro-2-methyl propane. This is just for reference I am giving you. 1-chloro-2-methyl propane and 2-chlorobutane. Both the molecular formulas are same. 1-chloro-2-methyl propane and 2-chlorobutane. Both are isomeric compounds, only chlorine substituted compounds. So here you see, to differentiate, they have taken the proton decoupled C13 NMR, and here they are getting 3 signals and they are getting 4 signals. So 2-chlorobutane or 4 carbons are non-equivalent. Therefore, you get 4 signals. In case of 1-chloro-2-methyl propane, 2-methyl propane, that means 2 methyl groups are same. Therefore, you will get 3 signals only. Similarly, 2-butane and 1-butane. Proton decoupled spectrum will give some problem, right? 1-butane and 2-butane. This is 2-butane, this is 1-butane. Actually, the print mistake. This is 2-butane. Here, instead of 2, you should have 1. Because both cannot be same. No? Both the names same, but structure is different. So here it is 2-butane, it is 1-butane. If you write 2-butane and check in 2-butane, how many non-equivalent carbons are there? 2 non-equivalent carbons, 1 acetylenic carbon and 1 CH3 carbon. And because that acetylene 1, 2 acetylenic carbons are same, 2 methyls are same. There is symmetry there. Therefore, 2 signals you will get. Here one is CH3 and the other is acetylenic. And you know, in SO4D of 2-butane, what is the pattern of multiplicity? 1 quartet and 1 singlet you get. Suppose if somebody asks you the molecular formula is C4H6. C4H6, and it gives 2 signals in proton decoupled C13 NMR, and it gives a quartet and a singlet in SO4D. If it gives a quartet and a singlet in SO4D, what is the structure? Then the structure is 2-butane. Again, the same question may be asked in a different way. 1-butane. You know, the same molecular formula C4H H8. Yeah, 3, 2. No, it's H6 only. Is it not? H6. CH3, CH2, C11, CH. So 6. C and H2N minus 2, right? So at 6, how many carbons, non-equivalent carbons are there in 1-butane? All 4 are non-equivalent. So 2 acetylenic carbons are there. The question can be framed like this: C4H6, and it gives you a quartet, it gives you a triplet, and a doublet and singlet. What is the structure? So it will be 1-butane, right? One butane and 2-butane. It's 2-butane. Actually, it's 2-butane only. 1-butane structure is it's there. 1-butane and 2-butane. This is 1-butane. You see, same thing. You know. Yeah, 1-butane. This is 1-butane. 1-butane spectrum. And this is 2-butane spectrum, and structures are this. See, in 2-butane, you see 2 CH3s are same, 2 acetylenic carbons are same. You get 2 signals as here. Okay. And here you see 1, 2, 3, 4. All are different. 1 CH3 is there, 1 CH2 is there, 1 carbon which is not attached to hydrogen, and acetylenic carbon attached to hydrogen. So here a doublet and a singlet, a triplet, and a quartet. This is what I asked in the that question. Okay. So you can differentiate 1-10 into. I'm just giving you a simple molecule, but it can be extrapolated for some complex molecules also for structural elucidation. Since you are just learning the basics, I'm trying to explain you with simple molecules. Okay. Because just proton NMR is sufficient to differentiate these two. But why we are taking C13 NMR? Just to explain to the difference, I am showing you these simple examples. Because unless we understand the simple problems, we will not be able to interpret or understand the complex problems. Now, it is also for differentiating isomeric alkenes. This is this structure, this structure, cyclooctatetraene. Under thermal conditions, yielded a dimer. A reaction was carried out before C13 NMR actually was not so generally routine. It was not. It came in. Actually, first proton NMR was developed and C13 NMR developed lately because of the sensitivity problem. And before that, this dimeric structure identification was difficult. For these three isomeric structures were considered like under thermal conditions. Cyclooctatetraene yields a product, and three isomeric structures were considered for this dimer, but they could not confirm it from the proton NMR. But C13 NMR spectrum of the dimer showed 4 signals. So 4 signals it gave. So which is the structure? You can compare all the three. Which of these 3 structures gives 4 signals? Here you see this, all are same. So 1, 2, 3, 4. Here planar symmetry is there. You see. So this and this are same. 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 Okay. In that, suppose if you take it this way, again one side is same as the other one. So 4 non-equivalent carbons are there. Therefore 4 signals. So the structure of the dimer was shown to be this structure, not this, because here the number of signals you can expect or more. You see here how many you can get? 1, 2, 3, 4, 5, 6, 7, 8. 8 signals. Here also plane of symmetry is there, but like this. 1, 2, 3, 4, 5, 6, 7, 8. Similarly here. 1, 2, 3, 4, 5, 6, 7, 8. So this and this give 8 signals, but whereas here it gives only 4 signals. And in the experiment also it gave this dimer, the product, what they got by the thermal dimerization of the cyclooctatetraene under thermal conditions, it showed only 4 signals in C13 NMR, thus confirming the structure of the product dimer. Till then there was ambiguity, means from the proton NMR they could not identify. And C13 NMR is also helpful in the structure assignment when there is ambiguity. For example, here you see warfarin. Warfarin is a rodenticide, and sodium salt of warfarin is an anticoagulant. Okay, warfarin is a rodenticide. It kills rodents, and sodium salt of warfarin is an anticoagulant. So their structure, just the difference here is OH and ONA, sodium salt and OH. So actually, normally we think both the structures are same. Like for example, phenol and sodium phenoxide, both the structures are same. Only in place of hydrogen, you have sodium, is it not? That's how normally we think. Normally it is considered. But in case of this, this special case, due to some intermolecular reaction problem, not problem, actually tendency of that reactivity. Of these groups, sodium warfarin is not OH, it's OH. Where R is OH. When R is OH, it is warfarin. It is rodenticide. So when there is OH, what happens? You have a carbonyl group in the side chain. So cyclic hemiacetal structure can be formed. OH can attack there, and then electrons go. So this can become OH. So giving you a cyclic structure. O and the bond is formed this between O and this carbon, carbonyl carbon, and a OH. That is hemiacetal structure. Remember, alcohols and carbonyl group, they undergo reaction to give you hemiacetal and ketol. Is it not? So similarly, enteromolecular hemiacetal formation is possible in case of warfarin, but there was no confirmation. In case of sodium salt, that kind of structure is not possible because there is no hydrogen. So here, if you observe, here carbonyl group is free. Here carbonyl is not free. It is actually, yeah, I'm showing you the structure, this one. Oh, this is the structure, hemiacetal structure. And actually this was confirmed. Warfarin shows signals like this: 100 ppm, 160 ppm, and rest all the same. Rest all structure is same for both. Only here there is difference. For warfarin shows 100 ppm signal, and sodium salt of warfarin shows 216 ppm. 216 ppm signal. Which one? Sodium salt. This one. Sodium salt shows this is observed at 216 ppm. Whereas in warfarin, we are observing 100 ppm. So what does it mean? In warfarin, carbonyl is not free. Whereas in case of sodium salt of warfarin, carbonyl is free. That is why it is observed at 216 ppm. And here also 160 ppm is there. Here also 160 ppm signal. That is cyclic ester carbonyl that will be observed in same place approximately at 160 ppm, at around 160 ppm. But the crucial signal is this one. 216 ppm signal is present in the structure of sodium salt of warfarin. Why? Because it cannot form cyclic hemiacetal structure. Whereas warfarin is not giving this signal, it is giving the signal only at 100 ppm, not at 216 ppm. Why? Due to the cyclic hemiacetal structure, cyclic hemiacetal formation of in case of warfarin. So that is how the structure of these two structures, these two compound structures were identified. So that what does it show? Warfarin and sodium salt of warfarin, they have got different structures. Here cyclic structure is there, here acyclic structure is there. So they have different properties also, because one is a rodenticide, the other one is anticoagulant. So it's very useful in tricky cases, special cases. Such structural assignment is possible with C13 NMR. And next, C13 NMR also is useful in conformational analysis. Like in Proton Nmr, C13 NMR also is very useful in the conformational analysis. Cyclohexane chair it will be, there will be flipping between different cyclohexane chair conformations via a port form. So they are rapid cyclohexane chair conformations. In fact, can be identified by low temperature NMR studies. Okay. Low temperature NMR studies. Because in cyclohexane, for example, methyl cyclohexane, you see, for example, eggshell methyl group in methyl cyclohexane is expected slightly off-field due to as compared to equatorial ice conformer. But at room temperature, there will be rapid flipping between eggshell conformer and equatorial conformer. But if we carry out low temperature studies, low temperature NMR studies, it is possible to resolve the signals of eggshell and equatorial methyl groups, thus showing that as cyclohexane, there is rapid interconversion between different chair forms. So like this, see. This is eggshell methyl, this is equatorial methyl, and at room temperature, only one signal is observed for both the conformers because there is rapid interconversion between one chair form to another chair form. So eggshell methyl is becoming equatorial, and equatorial again becomes eggshell. There will be rapid interconversion, and NMR spectrometer will not be able to see these two positions, these equatorial and axial position of CH3 separately. Therefore, it will give you an average value. Only that's the reason why only one signal is observed. Whereas, see, like this, at around 11 to 12, the signal was observed. Okay, no. This at room temperature only one signal at normal CH3 position, and at low temperature 2 signals were observed. One for equatorial methyl and one for axial. I told you axial is due to gamma Gaussian interaction, steric shift, and it will be observed slightly upfield than equatorial conformer. See, equatorial is coming at 20.8 ppm, whereas axial methyl is observed around 11 to 12. Actually, this will help, especially in studying the conformations. I mean, in cyclohexanes. For example, you just check if you have beta OH. That means, sorry, alpha OH here. Like say OH is there. It's not simple methyl cyclohexane. It is methyl cyclohexanol. We want to identify whether it is alpha or beta. OH is there, for example. So there it will be CH3 will be up axial, and from the chemical shift value, we can say whether OH is equatorial or CH3 is equatorial, cyclohexanol. So similarly, when it is bicyclic or tricyclic systems, the similarly you can do the we can study the stereochemistry, means axial and equatorial groups, etc. Okay. So similarly, dimethyl cyclohexane. So 1,2-dimethyl cyclohexane. Here also there will be rapid interconversion, and one is axial and the other one is equatorial. So equatorial becomes axial, axial becomes equatorial. Actually, this also is looking like equatorial. It is not equatorial. It's a drawing problem. It is axial. Okay, axial becomes equatorial, equatorial becomes axial. So 1,2-dimethyl cyclohexane normally shows 4 signals due to rapid interconversion, because this C1 and C2 same, C3 and C6, 1, 2, 3, 4, 5, 6, C3 and C6 same, and C4 and C5 same, because of the rapid interconversion, they are getting interconverted from one chair form to another chair form. And C1 methyl and C2 methyl, C1 methyl axial, C2 methyl equatorial, but due to rapid interconversion, they will not be, we cannot identify them, and we get the average shift. So at 40 degrees, only 4 signals are observed. And it's slightly less than 40, there will be like multiple patterns. Slowly the resolution takes place, but at minus 100 degrees centigrade, the interconversion slows down, and NMR spectrometer will be able to see all non-equivalent carbons separately. So you have 8 non-equivalent carbons here, therefore 8 signals are observed in case of 1,2-dimethyl cyclohexane. See, with the value, these are the values. See, C3 is axial 11.75, C4 is equatorial 20.3, C downfield shift, higher frequency. So you can study low temperature studies and identify the different stereochemical structures of various conformers. Okay. Similarly, you can identify, you can study geometrical isomers. Differentiation of geometrical isomers is also possible by C13 NMR. For example, you see trans-2-pentene and cis-2-pentene, E and Z forms. Here you see C1 methyl 17.9 here, because again here steric compression will be there, upfield shift, because of the closer proximity of this carbon and this carbon, slight upfield shift will be observed for this C and this CH3, though it is attached to double bond. Here it is away from this CH2, therefore strands position. So it will be slightly downfield 17.9. So from the chemical shift values of these values, we will be able to identify whether it is trans or cis, E and Z, etc. Okay, geometry differentiation of geometrical isomers also is possible by C13 NMR. And another thing is we can study reaction mechanisms also by making use of C13 NMR. Actually, we can study reaction mechanisms by making use of Proton NMR also. Again, I already told you C13 NMR gives the simpler spectra. So C13 NMR is quite useful in some cases. So what are the reaction mechanisms we can study? You can study aromatic electrophilic substitution reactions, aromatic nucleophilic substitution reaction, SN nucleophilic substitution, and stability of carbonium ions, formation of carbanions, etc. Okay. For example, aromatic electrophilic substitution reactions. So in aromatic electrophilic substitution reactions, normally the sigma complex is the proposed intermediate, and the formation of sigma complex is proved by Proton NMR also, and even in C13 by C13 NMR also it is proved. For example, you take hexamethyl benzene. In hexamethyl benzene, how many types of carbons are there? Only 2 types of carbons. All methyl groups are same, and all aromatic carbons are same. Is it not? See, all aromatic carbons, one signal, aliphatic CH3 carbon, if they will give one signal. So you get 2 signals, but we are interested in only one aromatic signal because that is the one which is going to be affected in aromatic electrophilic substitution reaction. See, this aromatic carbon is observed at around 205 ppm in case of hexamethyl benzene. But when it is treated with nitro NO2 plus, the electrophile, it forms a sigma complex like this. See, like this it should be this, and one carbon where the nitro group is attached is becoming sp3 hybridized, and all other carbons, I mean the positive charge is distributed on other 5 carbons. So sp2 carbon is becoming sp3 in the sigma complex, and all other 5 carbons are sp2 only, and that positive charge is distributed among all these 5 carbons. Okay, ortho and para will be more electron deficient. You know, you have seen the resonance structures of aromatic electrophilic substitution reactions, wherein after the attack of electrophile, ortho, because electrons are given to the electrophile, ortho and para carbons will become electron deficient, and it is distributed on all 5 carbons. So we call it a sigma complex. This one is sigma complex, and sigma complex is formed and this is the intermediate proposed in aromatic electrophilic substitution reactions. How it is formed? Like this, you know, nitro group is attacked and plus, now then again electrons shift there, and you get another resonance structure, and here these electrons shift here, and this here you get a positive charge. So that's the reason why I told you positive charge is distributed on these carbons. So all the 5 carbons are shifted downfield, and the carbon which is becoming sp3, that shifts upfield because the hybridization state is changing in the formation of sigma complex. See the value 98.7. The one which is attached to nitro, that electrophile, is becoming 98.7. From 205 to so much of field shift to 98.7. So that means the aromatic, that sigma complex is formed in this reaction. And observe the other carbons, the ortho 181.4, 29 para, downfield 201, 205, and even meta also more than benzene. Okay, so that means a formation of sigma complex is proved by C13 NMR in aromatic electrophilic substitution reaction. This is not nucleophilic. Aromatic nucleophilic substitution reaction. So here also sigma complex is formed, but in a different way. You know, sigma complex on on other 5 carbons, negative charge will be there because it is a nucleophilic attack. Nucleophile attacks the benzene ring, therefore electron density on the benzene ring is more, it becomes more, and in the sigma complex, all other 5 carbons show a field shift. See, for example, here you see 3 nitronuclear, because aromatic ring cannot undergo nucleophilic substitution reaction so easily because of the electron density and the aromatic ring. But by attaching some groups, electron withdrawing groups, the electron density is decreased. So in such cases, an anion, say methoxy anion, can attack and can substitute the hydrogen here. So like this, OCH3 is there, and here ethoxy and ethoxy group is attacking, and the negative charge will be on these 5 carbons. So here in this case, what's happening? Ethoxy benzene is taken, trinitro-ethoxy benzene. Now methoxy, sodium methoxide is substituting. That hydrogen is substituted by sodium methoxy. So methoxy group. So in both the cases, this is the intermediate that is formed, and actually a sigma complex is formed like this with a negative charge. So what happens here? Here also the aromatic carbons will undergo a field shift. So that we can identify by the C13 NMR. So similarly, we can study SN1 nucleophilic substitution reaction. So in SN1 nucleophilic substitutions, carbonium ion is formed. So that carbonium ion, it actually, it can be planar or pyramidal. Okay. Carbonium, because here, alkyl halide, that halogen is leaving, and this carbon plus. Now it can be planar or it can be pyramidal, and it is attacked by a nucleophile and to give you a racemic mixture. This is the normal reaction, SN1 nucleophilic substitution reaction. But to understand whether carbonium that is formed in SN1 nucleophilic substitution reaction is planar or pyramidal, we can observe, and we can confirm it by C13 NMR. If it is planar, it is sp2 hybridized. So sp2 hybridized, that coupling constant is normally in the range of 125 Hertz. Whereas if it is pyramidal, it is sp3 hybridized. So if it is planar, it is sp2 hybridized. So the coupling constant value will be around 168.5. If it is pyramidal, it is sp3 hybridized. So it would have been around 125 Hertz. We have seen methane, ethane, etc. Is it not? So what is normally observed? If we get coupling constant in this range, that means what? It is planar. If it is falling in this range, it is pyramidal. But it was shown to be planar by observing C13 NMR. This is the reaction that is going on. A planar structure is attacked by the nucleophile from both the sides. That will give you a racemic structure. That's a normal reaction which we have studied. So SN1 substitution formation of carbonium ions can be explained. And next, even stability of carbonium ions can be explained by C13 NMR. Stability of carbonium ions, for example, different carbonium ions are given here, and their chemical shift values are given. So which one do you think is more which is having more positive charge on the carbon? The one which is having more positive charge means it is more electron deficient. When it is more electron deficient means chemical shift value will be more. Isn't it? Downfield shift, because the chemical shift value depends on the electron density around carbon. Here more chemical shift means more positive character. Less chemical shift means less positive character. You see here in all these cases, which one is having more electron density, more electron deficiency? This one, tertiary butyl carbocation. Which one is having less, carbocation, less like electron deficiency? Carbocation character is less. In which case? In this case, because of the contribution of non-bonding electrons on the oxygen, the positive character on the carbon decreases here. So, which one will be more stable? Normally, if the charge is more, if the electron deficiency is more, it will be more reactive. More reactive means less stable, isn't it? More reactive means less stable. So, which one is more reactive here? This is more reactive because of the more reactive. So, 327.8 is a chemical shift, therefore more reactive, isn't it? Electron deficiency is more, carbocation character is more, therefore it is less stable. Whereas here it is carbonium character is less because of the stabilization. So this is most stable. Among all these, which is more stable? This one is more stable. Which is least stable? This one is least stable. So by observing the chemical shift values of various carbonium ions or carbocations, we can identify the stability. We can in fact put them in the increasing or decreasing order of stability and reactivity also. More carbonium ion character means more reactive. More reactive means less stable. Okay. Yeah. C13 NMR is also helpful to study the dynamic equilibrium between reactive intermediates in a given reaction pathway. For example, bromine addition. You know pretty well, cyclic bromonium ion is proposed. Okay. If it is not, hello? No? Yeah, cyclic bromonium and just 2-3 minutes, I'll be completing. Cyclic bromonium and structure is proposed in case of bromine addition to double bond. If it is a hello.
క్లాస్ అయితే లాస్ట్ క్లాస్
Any problem? Any problem? Hello. So cyclic bromonium ion structure is confirmed by the chemical shift value. Chemical shift of carbon in normal carbocation. If it is normal carbocation, it is 310, and sp3 carbon is 339. So carbonium ion is 310 and sp3 carbon is 39. But in bromination, the observed value is 174.5. So that shows it is not like this in dynamic equilibrium. It is in the form of cyclic bromocation. Okay, cyclic bromonium ion, and C13 NMR peak appeared at 75.6. Okay, this value. So if there exists dynamic equilibrium, the peak should have been at 175. This one, this average value. 310 plus 39, 340 divided by 2, it will be average value would have been this much. But since there is no dynamic equilibrium, the observed value is 75.6. That confirms the structure of, formation of cyclic bromonium ion in case of this bromine addition. Compare these values. Similarly, here in another case, actually this is carbon, not oxygen. carbon. In this case, you see there is dynamic equilibrium. That carbocation can be here, and this hydrogen can come here, and it can become here also. So their average value of chemical shift will be 204, and J1CH value should be 167.5. And the chemical shift and J1CH observed are this, which are in conformation with the dynamic equilibrium. In case here you just rectify this, it's not oxygen, it is carbon. And degenerate rearrangements can also be studied by making use of C13 NMR. You know, this undergoes a rearrangement. It just carbonyl is coming here, OCO6 is going there by a intermediacy of 6 member in this intermediacy of this structure. But this actually, since both the starting material and the product in this rearrangement are same, normally it cannot be identified. But if with C13 enriched sample, what happens? C double bond. Suppose if this carbon is enriched, carbonyl carbon is enriched, so you will have C13 carbonyl and also C13 carbonyl here. This also will be C13. So there will be homonuclear coupling. So if the rearrangement occurs, there will be coupling between these carbons, carbonyl carbon and S-toxic carbon. If there is no rearrangement, there will not be any coupling. But coupling was observed, that proving the degenerate rearrangement in this case, and this is the mechanism proposed. Okay, study of carbon ions also can be is possible by C13 NMR, and carbon ion formation increases the electron density. Electron density at carbon. Okay, so electron density increases means of field shift. You see, with ethyl magnesium bromide. So this is attached to magnesium bromide, MgBr. So it is a carbon ion character is there. That is the electron density is more. Simple. Actually, this is obtained from ethyl bromide. Ethyl bromide, the CH3 will not be negative value. It will have a positive value only because of the attachment of bromine. But when you when ethyl magnesium bromide is formed, that is Grignard reagent, it becomes more carbonyl character, therefore a field shift is observed. So by observing the carbon 13 NMR, we can identify whether a reagent is formed or not. And also the carbanionic character also we can identify. See, with ethyl magnesium bromide, the carbanionic character is less as compared to methyl lithium. Here, see, the value is minus 16.6. Methyl magnesium bromide minus 13.6. So which one will be more reactive? Naturally, methyl lithium, because its carbanionic character is more in, so organic metallic reaction, this is more reactive than this as compared to this, only when you compare these two. So we can relative strength of carbanionic character in organometallic compounds can be studied by C13 NMR. See, some of the problems or growth problems are given here. See, C5H11Cl. This is the molecular formula, and the data is given. So it is showing 5 signals, 1 quartet, 4 triplets, and we should identify the structure. The analysis also is given here. See, from the molecular formula and chemical shift range, it is haloalkane because molecular formula is conforms with haloalkane. So it can have 3 isomeric structures: chloropentane, 3 chloropentane, and 2 chloropentane. 1 chloropentane, 3 chloropentane, and 2 chloropentane. If you observe the structures, 1 chloropentane gives 5 signals, and 3 chloropentane gives 1, 2, 3, 4. Actually, this is wrong. Actually, here also again, this gives 3 signals and this gives 5 signals. Actually, structure, you please correct it in your books. This is taken from your book only. This is 2 chloropentane actually. Either you change the chlorine positions or number of signals. 3 chloropentane gives only 3 signals, 1, 2, 3. and 2-chloropentane gives again 5 signals. So based on the data, it is confirmed as 1-chloropentane. So like that. So again, another example I am giving you, C3H4O2Br2. Here it can be bromopropionic acid. Bromopropionic acid, but only 3 signals it is showing. One is at around the acid position 173.6, and it's a doublet. So 40.4 is a doublet. That means CH group is there, and one triplet 28.8. So it is CH2. So that means this structure is possible. So if it is CH3, CHBr, COOH, if it is CH3 instead of CH2Br, CH2COOH, if it is CH3, CHBr, Br can be there or Br can be here. But if it is not 1, 2, 3 bromopropionic acid, if it is 2 bromopropionic acid, we would have got 1 quartet, 1 doublet, right? But what we are getting? 1 doublet and 1 triplet. So here you see 1 doublet and 1 triplet. Yeah. Here also structure is problem. It's 2 bromopropionic acid. 2 bromopropionic acid. I need to, in the next class, I'll rectify it. You please correct it. It's not right. 2 bromopropionic acid. It is not 3 bromopropionic acid. Bromine should be here. Not okay. Not here. 3 bromopropionic acid only, but one is giving triplet. So it will not be doublet. It will also be a triplet because CH2, right? CH2. It will also be a triplet. So instead of D, you should have T here. So like that, some other problems are solved. You try to try to solve the structure. Problems which are in the end of your material. And some worked out problems are there. Some exercises are also there. You try it home, and if you don't get them, you try to discuss. Okay. Okay. That finishes. Here, this is the last example. I'll just explain you and wind it up. Molecular formula is C4H8O2. It is giving a singlet at 171.08. That means a ester carbonyl must be present, and it is giving a signal at 60.44. That means a carbon is attached to oxygen, and 2 quartets are there. 2 quartets means 2 CH3 groups are there. So 170 is C double bond O. And this indicates OCH2. So a C double bond O we have written, OCH2 we have written. 2 quartets means 2 CH3s. Just combine them, you will get what? Ethyl acetate. Ethyl acetate structure. It is the this is how you should confirm. You should analyze the problem. So just by looking at the data, you should see. So 179 means it is something. 2 oxygens are there, therefore it must be an ester group. So 171 is the ester carbonyl. Since you have 60 which is attached to carbon, this is attached to carbon. So COOCH2. So just from this you will have COOCH2, and you have 2 quartets. Therefore, to 1 CO, 1 CH3 is attached, and other OCH2, another CH3 is attached. So total 4 carbons are there, and this is the molecular formula. So that finishes, that will confirm ethyl acetate structure. So try to solve more number of problems, especially first the problems which are given at the end of the chapter. Those problems are to be solved first, and later on you can go for a little bit higher level problems. So that's about the applications of C13 NMR. That finishes C13 NMR. In fact, we need to discuss about F19 and P31 NMR and 2D NMR. Hope to discuss them in tomorrow's session. Okay. So that's all for today. Any doubts? Shall I leave? Hello?
Okay, thank you, madam.
Okay, if any doubts, you can just You can, write it down, and in the next class you can ask. We will discuss. Okay, we try to complete it in the next session. Next session, I will one more because 2D NMR may take a little more time. So tomorrow we will try to complete it. Okay.
Okay, thank you, madam.
Okay. See you tomorrow.